Okay, so here we're just moving on to have a look at degrees of freedom. When you're working with the chi-squared distribution, there is a parameter. There's only one parameter for the distribution, and that is the degrees of freedom. We use the Greek letter nu, which looks very much like a V, and this denotes the degrees of freedom. Degrees of freedom talk about how much the values that we're working with can vary. There are restrictions or constraints that we might need to consider that have a direct impact on how many values can vary or how the values can actually vary. So one of those restrictions, and the most popular restriction, is the fact that we know what the total of the numbers is going to be. Knowing the total wouldn't help me to know or give me any sort of indication what the first observed frequency would be, nor the second or the third or the fourth or the fifth. But when I do know those first five and there's only the last observed value left, I know exactly what it's going to be. Because the total number of trials is 120, the total of these observed values must also be 120. So I can do a quick calculation and figure out that 18 is the final observed value. This constraint, the fact that we know that the totals must agree, that the total observed frequencies is the same as the total expected frequencies, this is considered a restriction, and we reduce the degrees of freedom by 1. So the calculation in this case for the degrees of freedom is going to be V, I'll call it V. V equals 6 minus 1 equals 5. Which actually means there's only 5 values here that can vary. The 6th value is locked in immediately. 5 degrees of freedom. Okay, there are other reasons and other times where we will reduce the degrees of freedom. If we have to estimate any of the parameters that we use, we would also reduce the degrees of freedom. And technically, if we combine any cells together, if we combine any of these columns, we would also reduce the degrees of freedom. But I'll refer to that again as we get to each of those situations. Okay, degrees of freedom are important because they're going to help us to look up critical values for the chi-squared distributions that we're working with. Now, you can find those critical values in the formula book. I've put a QR code here that will take you instantly to the formula book. Or you can actually just Google an Excel formula book, and actually the new one comes up quite regularly. And we're going close to the back. If I'm correct, I think it's page 36. That has the table, the reference table of critical values that we need. So let's just have a look at how we would make use of these critical values. Okay, so let's just actually have a look at the table and see if we can track down, pinpoint some of these critical values. So if you notice in the table on the left hand side, that has different degrees of freedom. So the critical values are different depending on the degrees of freedom we're currently working with. And across the top, you'll notice some probabilities. So we need those two pieces of information to pinpoint a critical value. The chi-squared distribution typically has this shape. It has positive skew. When we're reading from the reference tables, the probability here is the probability in the right-hand tail. It's the probability that we exceed the critical value we're picking out. In this particular case, we're looking at 5%. So I want to know a critical value for the chi-squared distribution when we have 4 degrees of freedom that is exceeded by 5%. I'll start by picking out the 4 degrees of freedom row. And then I'm just going to cross-reference that with the 5% column. And we see right there, our critical value is 9.488. That is a chi-squared score that only has a 5% chance of being exceeded. Okay, let's do a similar thing. Chi-squared distribution with 5 degrees of freedom, and the percentage we're working with is 10%. What critical value is exceeded by 10%? We'll first pick out the right distribution. So we want 5 degrees of freedom. We're working in this row. Cross-reference the 10% column. And we see there we're looking at 9.236. That will be our critical value. Okay, and just again, here we've got a much larger value for the degrees of freedom. We've got 12 degrees of freedom. And I only want this critical value to be exceeded by 2.5%. So, going a little bit further down the table, here's the row with 12 degrees of freedom. We're going to look up the probability 2.5%, and that gives us a critical value of 23.337, quite a large critical value this time round. How about if the question was phrased this way? We want a value that is exceeded by 95%. 95% is quite a large percentage, which means we should be expecting a critical value close to 0, all the way down here on the left hand side. Let's track that down. We want the row with 6 degrees of freedom, the column with 95%, and that gives us a critical value of 1.635. So quite low, just like we expected. Okay, I just wanted to quickly show you a different form of notation that might be asking us to do a similar thing. So the probability that the chi-squared distribution is greater than y equals 0.95. So that will be depicted on the graph, or depicted on the diagram like this. I know which row to look at. I know which column to look at. Here's our critical value. 1.635. Okay, and just one more variation. What if we actually had to find the probability? So here, the probability that the chi-squared distribution is greater than 19.675, what would it be? Let's start with the row, which has 11 degrees of freedom. And I'm just going to read across until one of these critical values is 19.675. And I recognize that that is in the column represented by 5%. Okay, just one more thing to add on here. When we're calculating degrees of freedom, we need to be careful that our distribution, our expected frequencies all meet one specific criteria. And that criteria is that all of the expected frequencies or all the expected values must be greater than 5. For us to have a good fit for the chi-squared distribution, we do need all expected values to be greater than 5. So that means anywhere where they're not greater than 5, we need to combine values. We need to combine those columns. We need to combine the values in those cells. So looking at this set of expected values, I can see straight away the expected frequency for 8 is quite low. So I'm going to combine it with 7. I'm going to add these together since 8 was less than 5. And if I add them together, I get 0.09, which is still smaller than 5. So the frequency of greater than or equal to 7 is still too small. So let me actually try and combine all 3 of these cells together. So the frequency that is greater than or equal to 6, 0.64. It's still too small. I need to combine more cells together. How about all 4 of these? The frequency of being greater than or equal to 5 is 3.28. Still too small. So we just keep on going on until we get that frequency to be greater than 5. The frequency greater than or equal to 4 is 12.09. So that's the situation we want. We want all expected frequencies to be greater than 5. At this point, this is the first point, we should even try to find the degrees of freedom. I now have 5 expected frequencies I'm working with. 5 minus 1 gives us 4 degrees of freedom. Okay, so here's your chance to go and practice finding critical values, knowing that you can calculate the degrees of freedom and that you've looked at for whether or not you need to combine cells. Once you know the degrees of freedom, you're going to need to go to the reference tables in the formula book, or that you should by now have stored on your phone or laptop. And from there, you'll be able to pull up the critical values you need.